Alright, I think we're live. Welcome to another day of CMSC 341. Let's begin. As soon as I do one thing, let me save my little document. Okay. Here we are. So, how was the project? Horrible? Yeah. Well, Project 3 will be better. Project 3 and 4 will be not nearly as hard. If you haven't turned in Project 2, you can still turn it in today. If I've given you an extension, you won't have any penalty, but if I haven't given you an extension, it's still worth it to turn it in. It's only minus 10 points today, right? Thursday, minus 20 points Friday, minus 30 points Saturday. And it's still worth it to turn it on Saturday, even if you lose 30 points. If I don't give you an extension or whatever, make sure that you turn anything you have in, get as many points as you can on these things. It's a very important it's very important. So don't give up. If you feel really terrible about it, just talk to me about what to do in terms of extensions or whatever. Other teachers, I think, are being moderately liberal. Moderately liberal, yes, that's that is a term that makes sense. And so I will also be moderately liberal. So anyway, okay, I think that's really it for announcements. I'm going to try to grade the exam ones over this weekend. That's my hope. And so you'll have some idea of how you did there. Anyway, I think that's it for course announcements. And so, all right. And maybe I'll try to release a homework if I can at some point, maybe next Tuesday. So we had homework 1 and 2 were paper homeworks, and then we'll call homework 3 the early submission of the Discord tree. So it basically we'll call it homework 4. Will be another paper homework. It'll be about trees, probably, since that's what we know. We know about trees. Okay. So let's talk about. Well, okay. I guess first I should say I promised last time that I might do red-black deletion, and I've come to the conclusion that I'm not going to do that. And here are the reasons. One, no one remembers that anyway. If you really need to, I'm going to give you a PDF on how to do it. 2, we're past the tree project, so no reason to bother with red-black delete because really, red-black delete is no harder than binary search tree delete, except for the red-black fix-up on that, which is unfortunately not the same as AVL fix-up. It's a little hard to explain. There's a bunch of different cases. I'm just going to release a PDF for how to do it. And yeah, 3, it's in your real life. And what I mean by real life is after you leave college. Most likely you'll never hear the term red-black tree again, except kind of as a meme, right, of something that you might have had to implement in college. So, so I think it's good, right, because I've talked about the insertion case, which I think is something that you can kind of boil down into understandable cases where I could expect you to actually think through it, right? The insertion cases are kind of easy because you have, red uncle, and then you have, black uncle straight line, and black uncle, zigzag. And that's, there's 3 cases, and I've given them cutesy little names, and so they are moderately understandable. I'm putting moderately modifiers on everything. I don't know why. Okay. So, I'm not intending to rob you of red-black deletion. I am intending instead, we're going to talk about splay trees. Okay? So, you might ask yourself the question, what is a splay tree? Well, that's the whole point of today, so what is a splay tree? A splay tree. And so the answer to that question is, in a red-black tree, or an AVL tree, you notice that we have rules on balance, right? So in the AVL case, we literally maintain a height balance, and we do that explicitly, right? Mainly because we have a height in each node, and we keep track of that. We track it. If it's too far off, we run our little, they're called, the rotations in general are called something called Trinode Restructurings. You might hear that term in your life. Basically, the Trinode Restructuring is just the Zig Zig case versus the zigzag case of rotations. Okay? That's what it really is. So Trinode Restructurings, we've talked about those. We use Trinode Restructurings to rotate a little bit of the tree and to put it in the right form so that the heights are rebalanced. In a red-black tree, we don't, and this is the cool thing about a red-black tree, this is the thing I actually really like. In a red-black tree, you only have local data. And what I mean by that is that each node doesn't really know, it doesn't know much, right? It only has a little bit of info about itself. It doesn't know that, technically a node doesn't even really know about its children, right? It doesn't have any information beyond its own color. And I think that's kind of a cool little piece of information, a cool little thought exercise, because it shows you that actually trees can be mostly balanced, right? Because we talked about the proof that the number of nodes in the tree is bigger than or equal to 2 to the black height of the tree, right? Minus 1 technically. So the nodes in the tree is bigger than or equal to this. And so what this means is that basically what this means is like the depth of any node has to be less than something like 2 times the black height of the tree, which means, and so if you take the log of both sides, what the whole point of this argument, right, was basically that any operation is enforced to be O of log n, right? And what I mean by any operation is in, say, insert, find, delete, right? Any traversal operation, say anything that's in order, a post order, a pre-order, and say the clear, like a destructor, right? That actually does a traversal as well. Those are all O of n operations, but the point about those being O of n operations is kind of a silly point, because you have to visit each node once in any traversal. So once you run a traversal, you're not expecting it to be mega efficient like O of log n. The only point is that insert, find, and delete are kind of the primary operations of the tree. The traversal operations are used for deletion, for destruction of the tree, and usually for output, right? But we don't really consider them the primary purpose of the tree. And generally, you're only going to run the destructor once, so that's good. Whereas the insert, find, and delete operations, you could potentially run these 100 million times on any given tree. And so if you run these operations 100 million times, it's way more efficient to have something where you have O of log n rather than O of n. Of course, if you're running in-order traversals 100 million times, there's nothing you can really do. Okay, so that's the whole point of the red-black tree, is that the red-black tree uses only kind of local data. It only knows about itself, and it doesn't really know, like a red-black, you know, if you have a red node, it doesn't know how high it is in the tree. Even if you have a black node, it doesn't know how high it is in the tree. Basically, the nodes know almost nothing about where they are in the tree. They just know their own color, and that's it. And so it's kind of a cool thing, because it shows that you can get an almost AVL tree, right? It's a little bit more imbalanced than an AVL tree, but you can get an almost AVL tree, right? And this is the moral of the story. Without knowing heights, right? Now, you do have to know a piece of additional information, but that piece of information is, as they say, basically, what it really is it's like, it's a single bit, right? Where 0 represents, say, red, and 1 can represent black, or the other way around. Who cares which number you assign to which color? The whole point is that it's a single bit of information, right? Okay. So, and now you ask, all right, cool. You've reviewed all the balancing trees, but now you're talking about splay trees. So, what is a splay tree? A splay tree is kind of an interesting idea. What it does is it doesn't actually try to balance itself. So, a splay tree uses the Trinode Restructuring, like rotation business. But its goal is not to rebalance the tree itself. The goal is actually to make sure that any commonly used node ends up towards the top of the tree. Okay, so that's what the actual goal of a splay tree is: to make sure that any commonly used node ends up being towards the top of the tree. And so, of course, you ask, well, how do we do this? And so the answer is, well, simple. We just percolate any node. So if we let's say if we want to run if we run a find on a value, then so 1A, if we find the node, we splay it, which means just kind of percolating it up to the root. Okay, so what that means, and I'll show you what I mean by that in just a second. And 2A, or 1B, I should say, 1B, if we don't find the node, we splay the last node, null pointer that we did find. Okay, so you're going to splay something regardless of what you do. So if you're looking for a node in the tree and you don't find it, then you splay the last thing that you looked at up to the root. Okay, so then how do we run splay on an insert? So let's say now we're inserting. What do we do? And the answer is, just with every single binary search tree, insert as usual, right? Insert as usual, and then splay it, splay the inserted node to the root. Okay, so that's how you do that. So basically what we're going to do is, if we find a node, we splay it up to the root. If we don't find the node, we splay the last node we did find, again, up to the root. If we're inserting a node, it then becomes the root. So we're going to have to do a lot of rotations on the way back up in order to kind of keep pulling the node up, right? And so let me show you how that works in just a second. And then if we delete, you don't have to do anything for traversals. Traversals don't touch anything. So basically the only changes that we make are, so 3A, if we find the node, of course, remember, if we find the node and we are deleting it, we delete it, right? Which means we're going to pull a successor node up and all that kind of stuff. So what should I say? Yeah, if we find the node, we delete it. If the node was a leaf, so it didn't have any children, then splay its parent up to the root. And then basically, if we delete a node that isn't a leaf, right? If the node isn't a leaf, splay the node with the new value, right, up to the root. So basically, the moral of the story is we're always splaying, and then 3b, if we don't find the value to delete, do the same thing as we did for find. Just splay the last node we found up to the root. Okay. Alright, so now I've been using this, so it's kind of a bit terrible for me to do this, but I've been using this term splay a whole bunch, and it is a splay tree. So let's go over the cases of actually how to splay nodes, right? So there's really two cases. So there's really the Zig Zig case, and then there's the zigzag case. And then there's some other little cases that we'll go over in just a second, but let's ignore that. Okay, ignore. So right now, we're just going to go over the Zig Zig case, right? And so what does Zig Zig mean? Zig Zig is basically left, left, or right, right. Right, so that's how you should interpret this. They call it the Zig Zig case just because it's either left, left, or right, right. And you know that these two cases are kind of symmetrical anyway. So let's put some numbers in here. Let's say 5. Let's say 10. Let's say 15. Okay? And now whatever operation has happened before this, we don't really care. The whole point is, let's say that 5 is our special node. Alright, so let's color it, I don't know, teal. We don't really care about the other nodes. Let's call this one G for being grandpa. Let's call this one P for being parent. And let's call this one N for being the node. Alright? And so now, our only goal here, right, to splay a node means to make it the top node. Now, so there's basically two different ways to do it. You can either splay this node here, or I should say this, you can either rotate on node first and then rotate on parent. Or you can rotate parent up to grandparent, and then you can rotate the node up to the parent. And that's actually how they choose to do it. So let's go through how they, and by they I mean the inventors of the splay tree, right, the people who decided what the algorithm is. So the first thing that we're going to do, is we're actually going to rotate the parent up like this. Let me put on a nice little arrow. So what we're going to do, we're going to do this rotation, and now we're going to end up with, and let's copy paste. So grandpappy goes down here, becomes this child. And now, here's the thing. As I do all of this, you should remember that just because I've drawn this straight line, it doesn't necessarily mean that there aren't other children here. So you see how, oh, oops, I crashed my Inkscape. I'm a very bad human. Alright, so let's Inkscape it. Pull up the good news I've been saving, so maybe we didn't lose too much. Recent splay tree, wonderful. Look at that, we didn't lose almost anything. So basically we just need to, the same thing that I said before. We need to make node the top, and also we shouldn't assume that N, P, and G don't have other children, right? So don't assume that they don't have other children. The only reason why I'm drawing them this way is because N is the node we care about, P is the parent of that node, and G is the parent of that node, right? So that's what we're doing. So the first thing we're going to do, and hopefully this doesn't cause any problems this time. So behave well, please. There we go. So that's our first rotation, right? We're going to rotate the parent up, and the grandparent is going to come down and become the right child. In this case, I mean, of course, if it's the other way, then it will become the left child, and blah, 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 but who cares? It's all symmetric. And then the next thing we're going to do is we're going to rotate the node. And by the node, I mean we're going to rotate literally n, the node called n. We'll rotate that up. And so as we do that, what are we going to end up with? We are going to end up with this shape. And you might think, well, wait, we just introduced, like we took out an imbalance, right? This looks more balanced to us, and now we're introducing another imbalance. But remember that the explicit goal of a splay tree is not exactly to balance, right? The goal of a splay tree is to make n the top, right? And what I mean by the top is it's always going to try to be the subroot of its subtree. And then what you do is you keep making it the subroot of its subtree, right? Until it's the actual root of the actual tree, right? So, okay, cool. So this is the Zig Zig case. So the first thing we do is we rotate the parent up to the grandparent position. And then the second thing we do is we rotate the node up to the parent position, or grandparent position, right? We just rotate the node up. I don't care if you call it the old grandparent position or if you call it the parent position, because that's what it is intermediately, but who cares, right? So that's the point here. So we have the splay tree that starts off, the node is at the bottom, and here we end up with the node at the top. All right, so here we go. This is the Zig Zig case. And you basically have seen, you more or less have seen this case before in your AVL tree stuff, right? I mean, you haven't exactly done this because you'd be comparing heights, and of course, you probably wouldn't be doing this rotation and then this rotation, unless of course the heights were all mixed up and bad in this direction. Like if, I guess if a node was really heavy or really tall, and the grandparent on this side didn't have a whole lot, so it was kind of shorter, and blah, 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 blah. You might do this kind of rotation. But the good news is that you don't have to consider the heights, right? So a splay tree, if you notice, it doesn't need to know anything about any data around it. It doesn't have a color. I mean, of course, this node is teal, but there's no actual color associated with the node. This is just, I'm just showing you this as the node we care about, right? This is our current node. Okay. And now let's do the zigzag case. Okay, I don't want that one. I want this one. Give me this. And let's do the zigzag case. So as you can probably guess, the zigzag case is the different thing to the Zig Zig case. So it's where you have this structure, right? Or technically the symmetric structure where it's the parent and then the node kind of like the other way. But it doesn't really matter. So now with this thing, actually this works exactly the same way as the AVL. This is slightly different from the AVL potentially. You just have to remember to rotate the parent first. Normally in the AVL tree rotation, you're going to rotate the lower node first and not the upper node, but here you rotate the upper node first and then you rotate the lower node. So, you know, it's slightly different, but as you see, it's just made up of rotations. So that's the Zig Zig case. The zigzag case is, I'm going to say, exactly like the AVL case, right? And what do you know about the AVL case? In the AVL case, if you have a node, if you have an imbalance like this, right, the point is that what you're going to do is the first thing is you're going to rotate the lower node. So what you'll do is you'll do something like this, where you'll say dupe, dupe. And then what we'll have is that the got to remember to keep saving so that in case it crashes again. So the point here is that this is the first rotation that we do. But then you'll say to me, you know, but Eric, right? It's not the root yet. To which I say, you know, have patience. Have patience, right? We're not done yet. So, so the first rotation you do is you rotate the lower node up into the parent position, and then you rotate the node up again, and you end up with this kind of configuration. Okay? Something like that. All right. And so you see that these will get you 95% of the way. There's two little edge cases. So these are the two real cases. There's two smaller edge cases, and let me describe those to you right now. It's either the Zig case or the Zag case, and let me show you what those cases are. So you notice that what do we assume here, right? What we assume here is that the node has a parent and the node has a grandparent, right? Right, so we're assuming that the node has a parent and a grandparent. Well, what if it's only one node deep in the tree, right? That is a different situation, right? So technically, we have to consider this case here, where let's say this is the way it is here, and I guess the node was, you know, I'll just make the parent 10 so that the parent, so the original node's always 5, the parent's always 10, and the grandparent's always 15. But there's no grandparent, because in this case, P equals root, right? And so you might call this like the Zig case or something like that. And you might think, okay, well, how do I make this the root? To which you say, not hard. Just do a rotation, a single rotation, right? Just push this thing up to the root and you're done. So, I mean, you know, as I say, this is technically, right? Technically a different case because we don't have a grandparent. But as you see, you're like, well, I'm not very impressed. This is not like the most, you know, stimulating hard case that I could never have thought of, right? You think to yourself, yeah, this is something that, but it is an edge case that you have to think about, and you have to think about it when you're coding it up too, so I'll write it down like this. Okay, and then remember that this is the, this is like the Zag case, right? So this might be like Zig, and then this is Zag, right? So if this is Zig, we'll call this, say, Zag, right? And it's the same business. Instead of rotating to the right, here you'll rotate to the left, and you'll end up with something like this. All right, that's all. Splay trees are done. So, okay, so I think that what we should do now is we should run the visualization and just play around with it for a little bit, and then maybe we'll do some live coding. So let's pull up the Splay tree visualization. Okay. So let's insert 60. Let's insert 24. And so, okay. Now let's insert 16. Oh no, actually, let's get it to do a zag-zag case, or a zig-zig case, or whatever you want to call it. So let's put a pause on it, and let's insert, say, 72. So here what we're going to see is it'll insert as usual, right? That's regular binary search tree stuff. And then what we're going to do is we're going to say, 72 is the inserted node, 60 is its parent, 24 is its grandparent. So what are we going to do? Let's see what happens. Splay tree inserted element to root of tree. What? That's not... that sentence isn't quite right, but let's ignore that sentence. What it meant, I think what it means is splay the node to the root of the tree. Is that what it... it's a verb. It's not... I see. It's not splay has inserted an element to the root of the tree. It says splay inserted element. It's how you stress the sentence. So it makes sense now. So then it says zig zig left. So let's zig zig left. right? There we go. And now, of course, they do this in one step, right? But what we know secretly is that this is actually two different rotations, right? The first thing they did was they rotated the parent up, and then they rotated the 72 up. So just be aware that that's what they're doing. Okay, so let's do another. Say we're going to insert, let's say insert something in between, so let's say insert 68. The reason why I'm doing that is I want to insert something between the 60 and the 72. So I want to put something over here, and let's see what happens. So it inserts as usual because it's a binary search tree. And now this is a zigzag case, so 68 is going to come up to be the root, and so let's watch what happens. Here we go, right? And you see that, again, they're doing the two rotations in a single step. Now, it's always possible to do these two rotations in a single piece of code, but I tend to think it's better conceptually to think about them as two different rotations. All right, so let's insert 100 and see what happens. So let's insert 100, 100, 100. So now what we have to do is we have to rotate this guy up, so 72 will come up, and then 100 will come up. So notice that it is possible, right, to make, what should I say? It is possible in this kind of thing to make a linked list, right? These all have right children, but they're technically all null pointers, so the point is that it's always possible to make a linked list. Or I shouldn't say it's always possible, but it is possible to, through a creative set of insertions and finds and deletes, to make a linked list out of your data structure. And you know that a linked list data structure is generally bad because in this case this would be an O of n find, right? So let's find 24. So we're going to find 24. And remember that find actually does a splay as well. So if here, element found, so first thing we're going to do is we are going to zig zig it. There we go. And then we're in another zig zig case, so we're going to zig zig it again. And there we go. So notice here that this one, when you did this rotation, the cool thing is that when you rotated this one up, we got a right child of 72. 24 stayed as the left child, so 100 came here. And then when we rotate it again, because 24 has a right child, not a left child, 72 got this 60 child. So let's see that happen. So you see that 72 got the 60 child because of this, and now we're not quite in a linked list condition anymore. We have a little bit of stuff going on. All right. So let's do an element that you can't find. Let's say we're going to find, I don't know, 32. Find it. And so how do we find 32? Well, we go this way. 32 is less. And you see that when it fails to find, right? When it fails to find, what are we going to do? We are going to splay on 60, right? And now, why are we doing that? We're doing that because it was the last node that we visited before we went to its left child and didn't find anything, right? 32, if 32 is in the tree, it would have to be right here. But it's not here, so we go back to the parent and we splay on the parent. Okay, there we go. And of course you might say, hang on, that happened way too fast. But if you look at it, this thing is a zigzag case here. It even says it right here, zigzag left, but whatever, we can just look at it here. We see that if you trace this back, this is a zag-zig, right, or zigzag case. And so the issue here is that you know that you're going to rotate it this way, and then you're going to rotate this up, and so basically what's going to happen is when you rotate it to the right, it'll become the parent of 72 here, and then 72 gets the 68 child, so 72 will have 68 and 100, and then we rotate that up, so then 60 becomes the parent, 24 is the left child. So let's watch that happen. And remember, it happens moderately quickly because don't display both of the rotations happening, they just animate it as a single operation. So they just kind of percolate this thing up and then relink. Like that. Okay. And now we're done. Okay, so let's delete an element. Let's say we delete 72, right? Actually, let's insert a bunch more elements. So let's insert, say, 15, skip forward, 31, skip forward, 28, insert. I'm just inserting a bunch of elements until I'm happy, and then we'll delete something, right? I just want a bigger tree. So even if you're thinking like, man, I can't keep track of all this stuff, don't worry, I'm not actually keeping track of it either. Okay, so let's pick an element to delete. Who's a good element to kill? Let's say 52. Let's insert 52. Okay. Let's insert 61. Okay. So who's a good element to delete? I think 52 is a good element to delete, right? Or, I don't know, maybe 39. 39 is a good element to delete. And why am I picking on 39? I'm picking on 39 because it has a successor. And so we get to watch what happens when we delete this, right? So let's delete 39. So let us pause it and step forward. Okay. So we found 39, right? Look to the left subtree. Interesting. Maybe they're taking the predecessor. Element found. Splaying. Found node to root. Removing root. And then we splay the largest element in the left tree to the root. That's done. Ah, yes. So this is how delete works in a splay tree. So what just happened here? That's a good question. All right, let's delete another element and watch what happens. So let's delete 54. So notice what they're doing here. So what they're doing here is they are splaying the node up to the root. And you might ask, well, that's not exactly the binary search tree delete, right? This is different than the regular BST delete. But, you know, just be patient and think about what's going on here. So actually, this is a good example, because the next thing we're going to talk about probably, because the next project might have something to do with it, is what is it? It's basically leftist heaps. And so this actually works kind of more like a leftist heap in a sense, but we haven't gotten there yet. So we're going to kill off the root, and then you say, okay, if we kill off the root, what happens? And then what we're going to do is we're going to splay the maximum node up in the right subtree, or in the left subtree. And why is splaying the maximum of the left subtree make a new root? And the answer is because if you take the maximum of the left subtree, you know that it's smaller than everything in the right subtree, and you know once you splay it, it's therefore not going to have any right child. So you can just link on the right subtree to the right child of the maximum node. There we go. So now let's delete 101 and see what happens. So here we go. It's going to search for it. Searchy search. There we go. And then you see here, we didn't find the node. Okay, so we didn't find the node, so what it's going to do is splay the last one that we found up to be the root. Okay? And of course, because it's the maximum, and this is a good example of why being the maximum of the tree is an interesting property, if you splay the maximum of the tree up to be the root, then you know since it's the maximum, there can be nothing to the right, because everything to the right is bigger than whatever is in the value of the node. So let's write up the deletion algorithm a little more clearly, and maybe more correctly. So how does deletion work? delete work? The answer is step 1, you find the max in the left subtree. 2, splay it to the root. 3, delete it. 4, I'm sorry. Find the node itself. Not the, I skipped some steps. So find the node itself, splay it to the root, delete it. Then you find the max of the left subtree, right? Splay that to the top of the left subtree, and then 6, relink the right subtree of the old root to the right child of the left subtree. And you know, and the only thing to say is you know this will work, right? And by which, I mean, when I say work, it will be the right child will be null pointer. And the reason why the right child will be null pointer is because it's the max of the left subtree. So there can't be anything to the right of it. Okay. So I think the only thing left to do is to maybe code this thing up. What do you say? Let's code one of these. Let's see how far we can get today coding a splay tree. Let's make a new project. Let's call it Splay Tree 21, S21, or Spring 21. Let's make it in a new window. So I'm going to do some things that you haven't seen in your projects, which is another reason why I'm going to do this coding in class. So let's make a Splay Tree class. Okay, done. Why are you angry? Cool, you're not angry anymore. Let's fix this thing. I know, hang on, the screen will go blank for just a second, but just let it happen. Okay, there we go. Okay. Okay, we need a Splay Tree node class. Okay, or maybe let's just make it a struct for the simplicity of it. And so what are the types of things that we're going to need? So what I'm going to do, we're going to make a Splay Tree node pointer p left, p right, and of course, make sure I put a pointer on this thing so that it doesn't hate me. And then I'm going to do p parent, okay, which is something you haven't seen yet in your tree projects. And I'm gonna show you how to use parent pointers on a tree through this example. And then we'll have int value. Do I need anything else? P left, P right, P parent. I can't really think of anything. Maybe I'll do a default constructor. And then what we'll do is we'll just say P left, null pointer, P right, null pointer, P parent, null pointer, and then value, and then let's make it local local value, right? All right, I think that's good. So you've seen me create these kind of structs a billion times, right? So there's nothing terribly shocking about this struct, right? So we're not shocked. The only thing we're doing, the only difference, right? The difference is that I'm adding a parent pointer, and let's see how to make use of that. And so basically, you might ask, well, why do I really want a parent pointer here? And two of the reasons are deletion, and the other reason is that if you look at the Splay Tree cases, right? If I'm sitting at this node, I'm kind of interested in knowing who my parent is, and I'm interested in knowing who my grandparent is. And now technically you can always do there's some trickery you can do, like you can do a recursion where you pass parent pointers and all that stuff. You can do that. That's a way around doing this, but it's also possible, and we haven't really done it yet in this class, so I want to show you an example where you actually just have parent pointers. So what you get to do is you get to sit at this node and you can say, look at the parent, look at the parent, right? And that way we can head our way back up the tree without unwinding a recursion, without doing anything like that. So let's figure this part out. So what are the things we're going to need for Splay tree? Public, private, and so we'll need a constructor. I'm not going to make a copy constructor and assignment operator. You guys know how to basically do that. So boring. Let's do a destructor. Let's do a void insert into new value, maybe. Let's do a void delete. I guess we should call it remove int remval, maybe. Maybe a boolean find. Okay. And then here, all we really need to do is do something like Splay tree node pointer p root, maybe m root. Right? Is that really all we need? And of course, what we also need is we need some kind of display function. I'm going to steal the display function that I've been using for the other trees in just a second. So we'll do some kind of display function, but void display. Okay, we'll do something like that. All right, so that's good. That should be a pretty simple object, and by simple object I mean something that will struggle hardly to code. So let's do this. How do we code insert? How do we code remove? How do we code find? How do we code display? Well, who cares about display, right? Display is uninteresting. Splay tree. Splay tree. So let's do some fixing up of all of this stuff so that it's got its little resolution operator. Okay, now we can do mroot and hit that with a null pointer. Cool. And then here what we can do is we can call some kind of recursive delete on mroot. Right? So that'll be a helper function we're going to have to write. So we'll need that as a helper function. And of course, all of you have done this before for your other projects, so it's not terribly interesting, but it's got to be done, right? Where you say, you know, if not pnode, turn, delete, or recursive delete, pnode, p left, do it on the right, and then delete pnode, and then we're good, right? This should be it. Turn type void. I think that's all we need, right? Let's just add it in here. So there we go. Cool. All right, so done. Okay, so now we can do something interesting, right? So let's do insert, and I don't even think we need to do insert recursively because we're going to do parents. So let's do it this way. So we say Splay tree node p current equals mroot, and then we say while not inserted, and let's make a little little thing for, you know, bool inserted equals false, right? So let's go back to the iterative solution because we haven't seen that in a while. You've had to do two recursive insertions. So let's go back to an iterative insertion. So, okay. So what we're going to do is our standard thing, right? If new value is less than, well, first I guess we should say, I mean, we do have the edge case, right? So if not mroot, basically, right? Then we can just say mroot is equal to a new Splay tree node, new value, and then we're done. Return, right? Okay, so that's our little edge case for if it's a if we don't have a root. But let's assume we have a root now. So if we have a root, then we'll assume that this isn't null pointer, so pcurrent dot value, right? So then we say is now pcurrent is let's just do it this way. If pcurrent dot p left, then we can just insert it there, or I'm sorry, then we set pcurrent equal to pcurrent dot p left. Else we set pcurrent dot p left is equal to what do we set it to? New Splay tree node, new value. So let's just create the node. There we go, done. And now what we're going to do is what? So now that we've created the new node, I guess we need to display it, right? Let's set pcurrent dot p left dot p parent, right, equal to pcurrent, right? So we have to remember to set the parent. So that's the new little thing that we're doing here that we didn't used to do, is now we're setting parents. And okay, so now that we set the parent, let's set the pcurrent equals to pcurrent dot p left, right? And so what that does is it makes it so that pcurrent is the correct place to, we set, normally we wouldn't have to do this for a regular BST, but we're going to set pcurrent is the one to splay. So at the end of our insertion function, we're going to say splay pcurrent, okay? And then we'll have a helper function that does that. So, okay. What am I doing now? Else. And of course, at this point, we should say inserted equals true. So that'll pop us out of this loop. You can also technically, if you're brave enough, you can just use break, but you don't have to. All right, so else if pcurrent.p, right? Then we do pcurrent.p right, pcurrent.p right equals that, there, this, done. So all of this here is the standard iterative insertion without any recursion. Okay. All right. So nothing very shocking here, right? Okay, so now let's build this helper function, right? This helper function is basically the thing that's going to do 95% of the work for us, right? So we want a void splay on a splay tree node. So let's make that. There we go. And so now we have to detect our cases, right? So what are the cases that we have to detect? So let's do the edge cases first. All right, so remember what the edge cases are. They're the Zig case and the Zag case. Because in the Zig and the Zag case, what we'll know is that pnode dot pparent. Well, okay, so the first edge case is what if we are trying to display the root, right? If pnode is equal to mroot, return. Done, right? This just prevents us from doing anything terribly stupid. All right. Now, if pnode dot pparent, right? So we're checking to make sure the thing has a parent, and it will if we haven't returned here, right? The thing will have a parent if we haven't returned. What do I want to do here? right dot p left is equal to p node. Oh, actually, what I really want to do is I want to set this. So who cares about that part? We'll do that in just a second. So basically now what we're checking for is if the parent of our node is the root, right? So what the heck was that thing I just typed? And the answer is I'm going to paste it here. So if the parent is the root, and if the parent's left is equal to the node. So think about what this means, right? What this means is we're going up one level to the parent, and then we're coming back down on the left. We're testing if that's the p node, right? So if it's the p node, then what we're going to do is we are going to rotate, let's see, the thing is to the left, so we're going to make a right rotation on p node. On p node, maybe. And we'll set the thing that pops out as m root. Okay? And then else, we're in the Zag case. So this is the Zig case. And of course you're going to say, you haven't written the rotation functions yet. I hear you. I hear you. Okay, so that's how to do that. So now we're done with edge cases, right? So we're done with edge cases. So now we just have to do the regular cases. So we need to detect the difference between zig zig, zig zag, say zag zig, right, and zag zag. If basically I'm pretending that zag is equal to right and zig is equal to left, right? So I'm basically breaking it down into these 4 cases. And then we are going to have to figure out how we're going to do that. So, so let's say if oh, and then after we do this, we should return as well, right? Because we've made the thing the new root. Okay. So now let's pretend that this thing has a parent and a grandparent. I'm sorry, p node.p parent, right, is equal to .p left is equal to p node, right? So what this means is that the thing is its parent's left child, and then here you will be your parent's right child, right? So here you are the parent's left child, and then here you are the parent's right child. Okay, so those are 2 cases. Let's see. It probably is yelling at me. If statement has identical branches. Well, yeah, I haven't written any code yet. Give me a second. So, right, so now we have to detect, is the parent the left or the right child of its grandparent? Right, so let's find that out. So if p, let's assign Splay tree node pointer p parent, or the parent is equal to p node p parent, and let's say if the parent dot parent dot left is equal to the parent, then we know what? Then we know it's the same thing, right? Except we're at the parent level. So here, the parent is the left child of its grandparent, right? Else, the parent is the right child of its grandparent. So what do we do in each of these cases? So this is the left-left case, right? Zig zig. So remember what we do. The first thing we do is we rotate right on the, what do we do? We rotate right on the, oh, what do I do? What do I do? The node itself. No, on the parent. Right. Yes, 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 yes. Right, so we rotate the parent up to its grandparent position, and then we're going to rotate right again on the node, right? Okay? And there we go. That's the left-left case. Okay, now let's think about this case. What case is this? So the parent is the right child of its grandparent. So let's draw this out. So the parent, right, is, let's copy paste one of these things and then just like draw out exactly what case it is. That way we know what we're doing. Excuse me. So the parent is the right child. Okay. So the grandparent is over here. So just to make everything consistent, like this would look inconsistent if this was 15. So let's just change this to be 2. Right? So that this thing is on the right and this thing is on the left. So this is the current case. Right? So to fix this case, what we're going to do is we're going to rotate I'm sorry. No, I'm sorry. Yeah, well, I was right the first time. This one is the standard AVL tree rotation, so we're going to rotate the node up like this. We'll put the parent here, and then we'll rotate the node again. So we rotated the node right the first time, and then we'll rotate the node left. So let's do a right rotation. Okay, I need to be consistent. Rotate right on P node, rotate left on P node. Cool. All right. And now what I'm going to do is I'm going to copy paste this thing. Except we have to change the code. So we have to think about, if you're the parent's right child, right? If you're the right, then here we have to do a left, rotate left on the, okay, I didn't do this yet, so here we go. Rotate left on the parent, and then rotate left on the node. And then here, I think what we're going to have to do is we're going to have to do a rotate left. So this is the Zig Zig case, right? So we're rotate left on the node, and then rotate right on the node. So I think this should do it. Okay. And then I'm going to make a slight modification to this code here. So basically the point is, what I'm going to do is I'm going to say, we have to keep doing this, right? We have to keep doing this until P node is at the root. So instead of doing this, instead of saying if the P node is equal to the root, return, what I'm going to say is while the P node is not equal to the M root. And then we're just going to have a while loop here. There we go. So if it is equal to the root, then it just won't do the while loop. If it's not equal to the root, then it'll start doing stuff until it is equal to the root, and then there we go. So yeah, so this one, it's a long function, but you notice that it's not actually that complicated, because here's the zig case and the zag case, and then here's like zig zig, zigzag, zag zig, zag zag, right? So it's a lot of code because you have to split it in all the different cases, but in the end, whatever, right? So now we have to make a rotate left function and a rotate right function because we don't have those. Void Splay tree, rotate left on Splay tree node, pointer P node. Okay, have to do the same thing for a rotate right. And so these are a bit more annoying because we actually have to fix up all the parents. So I'll show you how to do that right now. There we go. So you see that we have some helper functions. So we're pretty happy with that. Okay. Okay. let's get the party started, right? So we've done our insert, boring. The only thing that insert does that's interesting is calls splay. Splay isn't boring. Splay is new, right? But we've seen a lot of these rotations before. We've seen a lot of this before too, right? Rotate left and rotate right. So how do we rotate left? What we're going to do is we're going to say the parent. And remember, basically the point here is we're going to rotate P node left and up into the parent position, right? So, okay. So rotating left means that, basically it means that the parent dot right is equal to the P node, right? So that's the point. Parent dot right is P node. So all right, that's not shocking. We're just going to declare something to be the parent. And then we need to, let's see, so we're rotating left. So what that means is we need to, when the parent goes down and this node comes up, we need to relink the right child of the P node, right? So P node dot P right is equal to the temp node, right? Okay. And maybe I'll just remember that auto in this case means splay tree node pointer. Okay, so in this case, what are we going to do? What we're going to do is we're going to say P node. Actually, we need one more. Auto grandparent is equal to P node. Let's say the parent dot P parent. Okay. All right, cool. So now there's a bunch of different options that can happen, and you'll see why I'm doing all this in a second. And you see that this is going to be a little bit more complicated than our standard rotate left and rotate right functions, just because we need a bunch of extra stuff. So, okay, let's do it. You see how I'm delaying because I'm always a little afraid of writing a rotation function. So what happens here? So we're going to say so we want P node dot P. So if we're rotating it left, that means that P node dot P left is going to be the parent, and then the parent dot P parent is going to be equal to P node. So this is what happens, right? We have to double every statement that we have. We have to relink not just the downward pointers, but the parent pointers as well. And so now, let's call this, oh crap, this is actually, we want this to be left, sorry. So now let's make right left, the parent dot P right is equal to right left, and then right left dot parent is equal to the parent. But remember that the parent is actually the, you know, it's the old parent. Okay, so the rotation is sort of done now. The only thing we have to do is we have to relink the grandparent. This is the hard part. Okay? And so what do I mean by the hard part? Well, there's three different cases that can happen, right? What if we rotate something up? So what if the grandparent doesn't exist? So if the grandparent doesn't exist, then what we've just learned is that the parent was the root, right? So now what we're going to do is say mroot is equal to P node, okay? So if the grandparent doesn't exist, then we just say the mroot is equal to P node, and then we're going to have to do this. P node dot P parent is equal to null pointer, right? And the reason why we have to do this is to prevent loopy conditions, where you could trace back up accidentally and say, what about the parent of the parent, or what about the parent of the parent of the parent, or the parent of the parent of the parent? And when you get to the root, you're going to have that problem, right? So that's why we have to set this to null pointer. All right. What's the other condition? The other condition is that the grandparent exists, right? Okay, so if the grandparent exists, there's two cases. If the grandparent .p left is equal to, it's still gonna, this is the problem, is that the grandparent isn't gonna see the rotation. The grandparent isn't gonna know what's gone on underneath it. So its left child is still going to be the parent, but we need to reset that. Grandparent .p left equals p node. And then otherwise it's the right child, so we can say grandparent p right is equal to p node. And then we need to fix up the parents, right? P node .p parent is equal to, actually, you know what we can do to simplify all this? We can just say this, and then we can just do this here. And keep in mind that if this is null pointer, it's okay, right? If it's null pointer, it'll be fine because it will work. And if it's not null pointer, it will also work, right? So we're doing this in every case. Okay, so you see that this is a bit more complicated, right, than the original rotation functions that we did for the AVL tree and the Discord tree. But whatever, right? Because we have the extra parent piece of data, we have to keep track who the parent's child relinks to, and so that's why all of this happened. Okay, so in order to do the rotate right function, I'm going to use the greatest feature in the history of features. We're just going to copy paste, and we're going to do left right like that. And now we just have to be careful that I don't do anything terribly stupid. So I'm trying to think, is that all I need to do? And of course I've renamed this thing left right, not right left. Is this code the exact same? If the grandparent doesn't exist, mroot is equal to p node. Yes. Grandparent.p left is equal to the parent. That doesn't change. This doesn't change. That doesn't change. This doesn't change. I think we're done. Yeah, I think we're done. So that was an easy function to write once we wrote the other one. Cool. All right. So, all right, so let's pretend all this works, and now let's write find. So remember how to find a node, right? Let's do a Splay tree node pointer. pCurrent equals mroot, right? And I'm going to leave the while condition blank for just a second. I'm going to have to think about what the while condition needs to be. I mean, obviously it's going to be like while not found, right? But we'll see exactly what we want the while condition to be in a second once we're finished writing this. So if the pCurrent dot value, right? And I always have to do it this way. Remember, if it's less, then we know we're going to go to the left. So and pCurrent dot yes, and pCurrent dot p left. So you might ask, like, why am I checking here? Why not just go left? And the answer is, if I just go left, I might end up at a null pointer, and a null pointer doesn't have a parent that we can trace back to. So remember what we have to do here. If the parent exists, but we can't find the node in the child subtree, then we have to splay the parent, right? So we may have to make sure we have to keep this stuff. So, okay. Well, let's make a bool, right? Found is equal to false. And so here what we're going to do is we're going to say pCurrent is equal to standard thing, pCurrent dot p left. There we go. and then we're going to say else pcurrent equals pcurrent.pwrite. And that is not exactly how we want to do this, right? So we need some more conditions. So if find val is less than the pcurrent.value, but not pcurrent, right? Or I'm sorry, not pcurrent.pleft. So there's no left child here. So what do we do in this case, right? So this is slightly different from the standard find. What we're going to do is we are actually going to break, okay? And the reason why we're going to break is because we want to punch out of this loop, right? And the reason why we want to get it out of this loop is because getting out of this loop means that we haven't found it, right? So what we're going to do is like while not found, right? And then we're going to return found at the end. But before we do that, we're going to have to splay on pcurrent, all right? Okay. So here we're going to have to go left. Here we don't go left because there is no node to the left. So what this means is the thing isn't in the tree. And so this is a decent use of break. I mean, you might say to yourself, but I've been trained never to use break. And the answer is use it sparingly. Use it when it's appropriate. And here's a good example of where it's, I think, appropriate to use break. Mainly because if you don't use break, then you'll have to write a lot more annoying code. So now we're just going to do the same kind of condition here, else if this, and the last condition is just an else break, right? So there we go. And here, I guess what we'll do. Oh. We never actually found the thing. There we go. So there we go. I think this covers all the cases, right? So yeah, this will get us there, and then all we have to do is splay on pcurrent. Now remember, if pcurrent, there's two possibilities. Either pcurrent will end up being the node we found, yay. Otherwise, it's going to be the parent of the node, but the node isn't there. So splay on it anyway, right? It's a splay tree, so we have to splay once per operation, so splay on it anyway. And that's how we do that. Okay. Yeah, so here, for remove, maybe we'll do remove next time. And then we'll do display next time. That should actually be pretty quick. Because we're almost done here. And then, of course, we have to test this stuff. So I might actually test, in the interim, before Tuesday, I might actually test that my rotate left and rotate right are doing the right things and that insert works. Because, as I say, I've just written this code, and it's always possible that it just doesn't work. And if it doesn't work, then I should fix it. Because, as you see, you just call splay on a pcurrent, and you expect it to run correctly. And if it doesn't run correctly, then we will be very confused. But yeah, so let's just remember, in the last minute of class, let's just talk about how we're going to do the remove. So remember what we're going to do. We're going to find a node. So we're going to have to, I think we're actually going to have to do, we're going to have to write some kind of find helper. And I might actually convert this into a find helper thing as well. Find the node, splay it, delete it, and then you splay, and then this is the weird one. You'll have to find the max in the left subtree. Or technically you can find the min in the right subtree. Both things are legal, but we're going to find the max in the left subtree because that's how we're going to do it, right? And then what you do is you rejoin the oh wait, sorry, find the max, but when I say find, I mean find and then splay the max of the left subtree up to the root of the left subtree. And then finally rejoin, right? So what we're going to do is we're going to rejoin the max, the left max, p right is going to be equal to the right subtree, right? Okay. So basically what we'll have to do is we'll have to do a Splay tree node pointer p node equals, say, we'll call it like node find rather than just regular find. And this node find is not, actually I guess it's fine if it splays, right? So yeah, so maybe it might even be fine if the thing splays. So let's have the helper splay as well. And then, so we don't need to splay it anymore. Then deleting it, right? So that's the thing. So we'll have to remember the two subtrees. So we'll say, right, the left subtree equals p node p left. And this is not the complete code, obviously. This is, we're going to have to fix this up. P node dot p right. So we get the left and the right subtrees, and then we're going to delete the p node, right? Cool. Let's put this here. All right. And then what we'll have to do is we'll have to write another helper function, right? Like a find max node in the left subtree. And maybe we'll have that splay as well, so we don't have to do that. And so then what we're going to do is just say, okay, well, whatever that is ends up, let's just have it return it as the new left subtree root, right? That'll be nice. And then all we have to do now is do the left subtree dot p right equals the right subtree. And that's it. So basically all we have to do now is write these helper functions for find, right? So I lied. This wasn't next time. This was this time. But yeah, we need to write the two helper functions, which I will leave for next time, because it's basically just rewriting find 2 more times, but it's just slightly different versions of find. And so that will be boring, but it'll take 5 minutes, and we'll do it next time. And then, of course, I will rewrite display, which just means I'm going to copy and paste from my old trees so that we get a nice little display function. And then we will be done. We can play around with it. All right, so that's it for today. Yeah, we actually coded a display tree in a day, in about, what, 40 minutes? So that's not terrible. Okay. I guess that's it for now. If you have any questions about your project, make sure you ask. Make sure you turn it in, even if it's going to be late. Talk to me about it. Get help, that kind of stuff. All right. I'll talk to everyone later.